and welcome to Acoustics Derivations. In this video, we will be deriving the reflection and transmission coefficients for oblique incidence between two fluids. I've drawn here on the right two fluids, fluid 1, which has a density ρ1 and a speed of sound c1, and medium 2 with a density ρ2 and speed of sound ρ2. And the interface here is at x equals 0. We have an incident wave coming at the interface at angle theta I from the normal, a reflected wave, PR, with angle theta of R off the normal, and finally, we have a transmitted wave, PT, at angle theta T off the normal. We're going to assume plane waves for simplicity, and we're also going to, once again, for simplicity, assume inviscid flow in the fluids. And I'll explain why we do that when it's important. Okay, so first of all, we are going to let our pressure field be time harmonic. So we have a pressure function of x, y, and t, but we're going to have it be time harmonic. So it's some complex amplitude p, capital P, function of x and y, times e to the j omega t. So it's time harmonic. And we note that as it's time harmonic, capital P can be denoted as some amplitude A times e to the negative j k vector dotted with r vector. Okay? So where r is vector is the position, and k, which I'll define here, is the wave number in a specific direction. So k is equal to k cosine theta e to the x hat plus k sine theta e to the y hat, where k is simply the magnitude of k vector. And as I said before, r is the position vector. So x e x hat plus y e y hat. Okay, well, so we can then write each of our PI, PR, and PT in this form. And we'll make the substitutions here. So we have that our incident field, we're ignoring the time harmonic nature currently. So we'll do capital P, the incident field can be written as the amplitude A of I times e to the negative j k x cosine theta I minus j k y sine of theta I. And I'm going to put a 1 on the k's to denote it's in medium 1. So take a moment to look at the figure here and try to see why both are negative. The reason is simple. Since we're plugging into the form e to the negative j k dot r, and our vector is positive in both the x and y direction, you can see here, going up and to the right, which is positive, of course, and plot. Then we just retain the negative because a positive vector dotted with a positive vector is going to be, or excuse me, a positive vector, yes, dotted with a positive vector is going to be positive. So there's the minus, and each of those terms are minus. Inversely, or differently, I should say, if we look at the reflected field, we have ARE. Oops, let me make that a little bit slower down so it's not confusing. ARE to the JK1X cosine theta R minus JK1Y sine theta R. And you can see here now, I can't show both portions at the same time, but since the reflected wave is going in the negative x direction, the x component of the exponent here is positive because it's a negative times a negative. But likewise, we still keep or like we did with the pi, we keep the y component still negative. Finally, we can look at the transmitted field. Just like that. And once again, this is going up and to the right based on the picture I've drawn. So they're both negative. And finally, I'm going to write that k sub n, either 1 or 2, is omega, so our angular frequency, divided by the speed of sound in each medium. And since we're looking at plane waves, we're only looking at one frequency. Okay, so to calculate the reflection and transmission coefficients and between two fluids at an oblique incidence, there are two boundary conditions that must be satisfied at the interface. The first of which is that the pressure on both sides of the interface be equal. Otherwise, if this weren't the case, it turns out that the interface, which we've assumed to be massless here, would experience an infinite acceleration, which is unphysical. The second boundary condition, which might be a little less obvious, is a continuity of normal particle velocity across the interface. So once we have established the two boundary conditions, we can use them. So our first boundary condition, BC1, was a continuity of pressure. So this says that the pressure at the interface of the incident wave plus the reflected wave must be equal to that of the transmitted wave. You think right on the interface. Well, so this is at x equals 0. Let me be clear about that. And since they're all time harmonic, as we've assumed, we can write this just in terms of complex amplitudes, capital P. Okay, now we substitute our expressions for capital P, noting that x is equal to 0 in each. So all the x equals 0 exponents just become 1. So they go away essentially. You're multiplying the rest of the expression by 1, and you obtain the following. Okay. So it turns out that this relation must hold everywhere along the interface for an arbitrary value of y. In other words, the wavelength along the y-axis is the same for each of the components. You could say it differently, that the spatial periodicity, cannot change. So in order to be satisfied by all values of y along the interface, satisfied for all values y, the following must hold. Well, there must be k1 sine theta I is equal to k1 sine theta r, which is equal to k2 sine theta t. You can see the only way that this expression is true is if the exponents are all equal. And the only way they're equal, I should say equal for all values of y, is if these expressions hold. Now, this set of equations, or equalities, I should say, give us two very, very important results. The first is known as the law of specular reflection. If we look at medium 1, we see that K1 is equal in both of those cases. Therefore, sine theta I must be equal to sine theta R. In other words, sine theta I is equal to sine theta R. So what does this say? Well, other than sine theta I is equal to sine theta R, or theta I is equal to theta R, it says that a wave impinging on an interface at an oblique angle will be reflected at that same angle relative to the normal. In other words, you can think of it as an angle in equals angle out sort of situation. The second result this set of equalities gives us is very, very famous. Not that the law of specular reflection isn't famous, but I would argue this result is more famous. It's Snell's law. Well, we see that sine theta I over C1 is equal to sine theta t over C2. Why have I used C1 and C2 instead of K1 and K2? Well, remember that in both mediums, the angular frequency is the same. So the angular frequency would cancel on both sides, and you're left with this result. Okay. Well, if each exponent here is equal, if each exponent here is equal, that must mean that AI plus AR is equal to AT. Okay. AI plus AR is equal to AT. Oops. AT. So once we have this expression or this equation, we define the reflection and transmission coefficients. The reflection coefficient is defined as AR over AI, which is the reflected amplitude divided by the incident amplitude. And the transmission coefficient is the transmitted amplitude over the incident amplitude. When we write it in this fashion, we can divide this whole equation, or I should say each term in this equation, by AI, and we obtain 1 plus R is equal to T. And so we'll need this expression to be able to actually calculate what R and T actually are, get an equation for them rather than just the definition. So I want to pause for a second before we move on to the second boundary condition and note there's an equivalent way to explore this first boundary condition or the result of this first boundary condition. And that has to do with the trace velocities along the interface. If we're looking at this expression here, it turns out that the trace velocities along the interface must match. Well, what's a trace velocity? Well, the trace velocity is the apparent speed with which a point on the waveform travels along the interface. So you can kind of think of a wave coming in, let's try to draw something like this. And as the wave comes in on the interface, there'll be a point on the interface that goes up, in this case, with the pressure fluctuation corresponding to the incident pressure wave. So the apparent speed at which this wave or this waveform travels along, in this case, the vertical axis, that's known as the trace velocity. And it turns out the trace velocity on the incident in medium 1, so from the incident and reflected, is equal to in medium 2 with the transmitted. And so let me write that over here. It turns out that the trace velocity is given as omega over k1 sine theta I, which is equal to omega over k2 sine theta r, excuse me, k1 theta r, which is also omega over k2 sine theta t, which you can once again obtain the law of specular reflection and Snell's law. So both of these two explanations, and this I was not very rigorous in the trace uh, speed, with trace velocity uh, calculations, but if you were to go along this path instead of the path we took over here, the results are still the same, as they should be. Physics should be consistent with itself through different forms of derivation. So once we've obtained this expression here, we can now move on to our second boundary condition, which is the continuity of normal particle velocity at the interface. And you might be asking, why only the normal particle velocity instead of the particle velocity in general? Well, we assumed at the beginning that we're looking at inviscid flow in the fluids. And it turns out that the tangent component, i.e. the vertical component, uh, in this case, of the particle velocity need not be continuous because of that assumption of inviscid flow. The reason being a velocity shear generates no force in the inviscid flow. So we don't have to worry about it. So if we define, uh, just like we had P be a function of capital P times e to the j omega t, we'll do the same for u, for particle velocity. So little u is equal to big U times e to the j omega t. In other words, some complex amplitude u times e to the j omega t. Okay, and then when we apply the condition of the normal particle velocity at the interface, we just take the x component. We just take the x component of particle velocity, not the y. So we have that the incident particle velocity plus the reflected particle velocity is equal to the transmitted particle velocity, once again at x equals 0. Now we recall the linearized momentum equation, in this case in 1D, which is given by this expression. And I'm relating here just the complex amplitudes. Thus, at x equals 0, if we make this substitution, we obtain 1 over rho 1. I should say make the substitution of each one of these expressions, each u, and write them each in terms of the derivative of pressure we obtain. So we obtain this expression here. And the negative 1 over j omega in each term cancel. But since the densities are different from your field or your fluid 1 and fluid 2, those cannot cancel. Okay. Now, once we have this expression, we recall our equations for pressure, or the pressure, the complex pressure amplitude, PI, capital PR, capital PT. And we'll just simply take the x derivative of each of them. So dpi dx is equal to negative jk cosine theta I is k1 times pi, because it's a complex exponential, or just an exponential in general, like e to the something. dpx dpr dx is equal to positive jk1 cosine theta r pr, and dpt dx is equal to negative jk2 cosine theta 2 pt. So I'm going to skip a little bit of the math here because it's a little bit tedious, but what you do then is you take these expressions and you plug them into there. And then evaluate. So you plug in, you evaluate then at x equals 0. You cancel the omega term, or the omega in each term, I should say. And then recall that what we looked at above, k1 sine theta I plus k1, excuse me, not plus, equals k1 sine theta r equals k2 sine theta t. And that's done. We recall that so the exponents or the exponentials cancel. And we also know that theta I is equal to theta r. So if you do all that, which it's a little bit of work, but it's relatively straightforward, you obtain that cosine theta I over rho 1 C1 times AI minus AR is equal to cosine theta t over rho 2 C2 times AT. Okay? And now we recall what our definition for the reflection and transmission coefficients are, given here. And we can write this expression then. If we divide, well, first let me do this. So let's divide cosine theta I rho 1 C1, or move it to the other side. So we have AI minus AR is equal to rho 1 C1 cosine theta t over rho 2 C2 cosine theta I times AT. Well, now we apply our definitions for R and T, and we obtain 1 minus R is equal to rho 1 C1 cosine theta t over rho 2 C2 cosine theta I times capital T. Okay? So now we have two equations. Here's the first one, 1 plus R equals T. And then 1 minus R is equal to rho 1 C1 cosine theta T, rho 2 C2 cosine theta I times T. So we have two equations and two unknowns. It's a little bit tedious once again, but you simply solve the system. In fact, let me write the other one, 1 plus R equals T. And I'll leave this as an exercise to do yourself. It doesn't really tell us anything physical, and it's not necessarily hard or have any fancy tricks. It's just a bunch of algebra. So I think you can do that. And if you do that together, you solve the system, and for R and T, you yield that R is equal to rho 2 C2 cosine theta I minus rho 1 C1 cosine theta T over rho 2 C2 cosine theta I plus rho 1 C1 cosine theta T. And you also obtain then that T, the transmission coefficient, is 2 rho 2 C2 cosine theta I over rho 2 C2 cosine theta I plus rho 1 C1 cosine theta t. And now if you're extra brave or you want an extra fun um, time with some math, you can add these together and show that 1 plus r does in fact equal t. Lovely. So sometimes when you're looking at reflection and transmission problems, for example, an impedance tube, you're looking at normal incidence. What we have here is oblique incidence. Well, normal incidence, if we scroll up, normal incidence, we assume that theta I and theta R are along the x-axis, and theta t is also along the axis. Or I should say pi, pr, and pt are along the axis, which makes the angles 0. Well, if we know that cosine of 0 is 1, so if you plug 1 everywhere you see a cosine term, then you get, for normal incidence, you get R is equal to rho 2 C2 minus rho 1 C1 over rho 2 C2 minus plus rho 1 C1. And you get T is simply 2 times rho 2 C2 over rho 2 C2 plus rho 1 C1. Okay, so now we have that. I want to mention that when we were looking at the continuity of normal particle velocity at the interface here, we could have also written it in a different form. So if we had written, let me do a line here to differentiate. If we had done the normal particle velocity, so when we're looking at it, we could have considered also a cross-sectional area of a bundle of rays, or perhaps the beam width of bounded waves. So if I were to draw a picture here, instead of a ray, we could have had a bundle of rays. For example, this is our ray bundle, or our bounded waves, the finite width of our incident wave. And here's the interface. We have our reflected waves coming off with, try to draw this a little bit better, like this, where each of these, if I were a good drawer and not drawing on a trackpad on my computer, these widths should be the same, which we'll call SI. And this also you could write as SR for the reflect, but it turns out that they're the same based on the arguments we looked at previously, the law of specular reflection. And I'll show that in just a moment. And so, and we also have our transmitted wave. So I've drawn all of the bounded waves, finite beam widths, or bundle of incident rays, however you'd like to think about that. So instead of just the one ray or the plane wave that we looked at before, and then we have a bundle. And at the interface, we can kind of see there's this right here, which this is a delta Y. It's the width of the interface between, or the width of where the beam is impinging upon the interface. So you can see that it's greater than SI because SI would be here. This is SI. I'll confuse you here. So this, the dotted line here is SI, and you can kind of think of a triangle. So delta Y, your delta Y is greater than the width of your incident wave packet or bundle of rays. So one final note before we return to the normal particle velocity, we'll say that the incident, or we'll note, I should say, that the incident bundle is some LZ, which I'll define in a second, times delta Y times cosine theta I. And again, this is equal to SR. ST is equal to LZ times delta Y cosine theta T. So this SI and ST, so this is giving you a relation between delta Y, your cosine of your angle, and SI. And it's an area, not a line. So that's where LZ comes in. LZ is the depth of the bundle in the Z direction. Not very interesting, but it makes the units check out. So if we have this formulation and we return to our normal particle velocity, we could have written the continuity of normal particle velocity as our particle velocity times our cross-sectional area on the interface. In other words, this is actually the volume velocity, a continuity of volume velocity. Let me write that. So instead of a continuity of particle displacement, we have a continuity of volume velocity. If you see here in R and T, or rather I should say here, 1 minus R rho 1 C1 cosine theta T over rho 2 C2 cosine theta I T. And you note that rho 1 C1 is equal to your characteristic impedance Z1, and rho 2 C2 is equal to your characteristic impedance for the second medium, so there's the first medium and the second medium, Z2. Then we can see that 1 minus R equal to rho 1 C1 cosine theta T over rho 2 C2 cosine theta I times T is very, very, or is not very, very, it can be written as noting this here, SI and SR. This can be written as Z1 over cosine, or excuse me, Z1 times cosine theta T over Z2 cosine theta I times T. So we haven't used over here. I misspoke, apologies. Now we invoke what theta I and theta T are. And so the left-hand side can become Z1 over SI divided by Z 2 over ST. If you think about it, do the math, noting that LZ and YZ are canceling on top and bottom. And if you were to do, well, one final step, we note that Z1 over SI is really the acoustic impedance of the first medium, and Z2 over ST is the acoustic impedance of the second medium. Well, if we note both of that and plug those into here, then we can obtain once again expressions for R and T in terms of the acoustic impedance, or in terms of acoustic impedances, rather than the characteristic acoustic impedances that we had before. Okay, so you might see the expressions for R and T in this form. Finally, there's one more thing to note before we close, and that's the power reflection and transmission coefficients, not to be confused with just the reflection and transmission coefficient. We'll define the power reflection coefficient, R, little r, as the power of the incident wave, excuse me, the power of the reflected wave divided by the power of the incident wave, which, if we're thinking of a plane wave, we can know the power is simply the intensity times the cross-sectional area. And we know that SR is equal to SI. Therefore, R is equal to, well, now we ask ourselves the question, what is, so if these are SR is equal to SI, then these cancel. So then the question is, what is intensity? Well, we know that for a plane wave, it's PRMS squared divided by the characteristic impedance of the medium, rho naught, C naught. So we have that it's PRMS of the reflected wave squared over Z1 divided by PRMS of the incident wave divided by squared, excuse me, PRMS of the incident wave squared divided by Z1. Well, the Z1s cancel, and any time dependence of PRMS cancel. For the instant wave and reflected wave cancel, and all that you're left with is, because the spatial at the interface, the spatial dependence also cancels. So all you're left with is AR squared divided by AI squared, or the magnitude, which then we recognize as the magnitude of R squared. Well, similarly, we'll define the power transmission coefficient as WT over WI. So power of the transmitted wave divided by power of the incident wave, which is going to be, once again, ITST over IISI. But now SI and TI are not equal. So we'll substitute in our expressions for I that we discussed above, or for intensity. But now we recognize what ST and SI are. So this is another reason we looked at this formulation, not only so we could formulate our reflection and transmission coefficients in terms of the acoustic impedance, but also in terms of, or so also we could find the power, reflection, and transmission. So we need SI. But we know that we have an SP divided by SI. So the LZ and delta Y are both going to cancel. And we're going to be left with, if we move the characteristic impedance of the medium around, we're going to be left with Z1 cosine theta T over Z2 cosine theta I times AT squared over AI squared, which we recognize this expression here, or this term here, to just be magnitude T squared. Often you'll see tau as simply equal to 1 minus r, which is 1 minus magnitude r squared. So this helps you calculate the power, reflection, and transmission coefficients. So this was a bit of a long video, so let's quickly recap. So we looked at reflection and transmission for oblique incidence. We assumed a plane wave with an inviscid flow. We had an instant wave, a reflected wave, and a transmitted wave. We assumed first a continuity of pressure, and that allowed us to derive the law of specular reflection and Snell's law, as well as the relation 1 plus r equals t. Then we used our second boundary condition, the continuity of normal particle velocity at the interface, which allowed us to derive the second expression, second equation, 1 minus r is equal to rho 1 c1 cosine theta t over rho 2 c2 cosine theta I times t. That, with our first equation, 1 plus r equals t, allowed us to find our reflection and transmission coefficients, which are given here. Then we said, okay, what if we kind of reformulated the question a little bit, or thought a little bit harder about what's going on at the interface, including some areas. And that allowed us to show from the continuity of volume velocity that we can write our reflection and transmission coefficients in terms of acoustic impedances. Finally, we derived the power, reflection, and transmission coefficients, which are shown here. So that concludes this video. Thank you.